Okay, we're going to begin our discussion of solving trigonometric equations. Now we'll look at a lot of examples, but as we're looking at these examples, we need to be developing a strategy when we see an equation. And so we're going to start out with the simplest types of equations. And you can see here what we're supposed to do is we're supposed to solve for theta. In the equation, 2 times the sine of theta plus 6 equals 5. Furthermore, we're supposed to find theta values that lie between 0 and 2 pi. That is, 0 is less than or equal to theta is less than 2 pi. So, and we'll talk about that here in a moment. But we need to start the idea of classifying these equations. And if you'll notice in this equation, we have one single trigonometric function, sine of theta. And that trigonometric function only has one appearance, period, in the equation. So let's just kind of notice that's kind of the idea that we've got here, a single trig function in the equation that occurs only once in the equation. Only once. So we have one trig function that's sine of theta and it only appears at one time. Now, the strategy when we have an equation of this type is to isolate. Now, we're actually looking for theta, but we first have to think of where theta is tied up, and it's part of the sine of theta. So we need to isolate sine of theta. It's kind of like thinking of sine of theta as the x value, and we're solving for the x value. Now, that won't tell us what theta is, but it will tell us what the sine of theta is, and from there, we'll figure out theta. So as we're solving, we need to isolate. Okay. Here's how we're going to, I'm not writing the solution, here's how we're going to do it. We're going to take our equation, and we're going to solve for sine of theta. So that's our strategy. Solve for the sine of theta. And after that, we'll figure out what theta is. So we need to isolate sine of theta. That means we need to subtract a 6 on both sides. So we'll have 2 times the sine of theta is equal to 5 minus 6. And of course, we know that's negative 1. So we have 2 times the sine of theta is equal to negative 1. Now, we'll continue trying to solve for the sine of theta, so we need to divide out the 2. When we divide on the left side by 2, we'll be left with just sine of theta. When we divide on the right side of 2, we'll be left with negative 1/2. Okay. Now, we don't know the value of theta yet. What we know is the value of the sine of theta. So the way I approach this, and I recommend that you do the same thing, I'm going to draw myself a representative unit circle. Unit circle. Okay? Understand what that means. Now, here's first the idea of why we have the statement up here. We start considering angles of 0. And then we go around the unit circle and say, okay, what angles anywhere around the unit circle of 1 revolution will have a sine value of negative 1/2? Now, once we get to 2 pi, we start repeating, don't we? And of course, we'll have an infinite number of angles because we can go around and around and around, or we can even go to the left, so we would have negative angles. So there's actually an infinite number of thetas that make this true. But we're only looking for the thetas in a single revolution, a positive revolution around the unit circle. So here's the way I approach this then. The sine of theta is negative 1/2, and along the unit circle, the sine of theta is represented by the second coordinate. And the second coordinate is along the vertical axis, isn't it? So here I'm thinking, okay, well, that's roughly where negative 1/2 is. Okay, well, under those circumstances, then, there's a point on the unit circle that's here, okay, that has a negative 1/2 second coordinate. And so the angle that, whoops, I didn't draw that very well, did I? The angle that we need to figure out that angle, but remember, that's the angle that comes clear around like this that we're talking about. And then there's another position over here that has a second coordinate that is -1/2. Now, say the second coordinate is -1/2. Well, that would be the angle that I'm drawing there, and that would be calculated here. Now, because we know 1/2 and -1/2 are the results of taking the sine of some special angles, and we may recognize that the angle in here is the same as pi/6, then we're pi/6 short of 2 pi. In other words, if we go if we took 2 pi and subtracted pi/6 from it, that's where we would be here. We're pi/6 short of going all the way around. And we could think of that in a lot of different ways. We could say, okay, here's 1 pi/6, here's 2 pi/6, here's 3 pi/6, here's 4 pi/6, here's 5 pi/6, here's 6 pi/6, here's 7 pi/6, here's 8 pi/6, here's 9 pi/6, here's 10 pi/6, here's 11 pi/6. And so this is actually at 11 pi/6, which is in fact 2 pi minus pi/6, because 2 pi is 12 pi/6, and we're subtracting pi/6, so it gets us at 11 pi/6. Now we also pass this position, which is 7 pi/6. Now another way to have thought of that is that we're pi/6 beyond pi. So if we take pi and add pi/6 to it, we will get 7 pi/6, because pi is 6 pi/6, and we're a pi/6 in addition to that, which is 7 pi/6. So I probably wouldn't have counted it off like I did, but I would have calculated in the fashion that I've calculated here. But the bottom line is that theta is 7 pi. The solutions would be a value of 7 pi/6 and a value of 11 pi/6. If we take the sine of either one of those angles, we get -1/2, and those angles are between 0 and 2 pi. And there are no other angles between 0 and 2 pi whose sine is -1/2. So our solution, there are two solutions that satisfy the equation for the parameters that the solutions between 0 and 2 pi. Okay. Well, that's the approach. So let's extend now and look at something, and we'll do another problem. Well, let me write down the problem. So we're to solve the equation 12 times cosine squared theta equal 9. And we're to solve over the same interval from 0 to 2 pi. It can include 0, or theta could include 0, but not 2 pi. So those are and that's basically one revolution around the unit circle. So notice here, of course, it's a different equation, but we still have one single trig function, and it occurs only one time. This time it has an exponent of 2 on it, but one function that appears one time in the equation. So we still go about the idea of first solving for that function. So what we're trying to do here is isolate and solve first for cosine squared theta, and then from that solve for cosine of theta. So we're trying to solve for cosine theta here. And then we'll figure out theta from there. So when we take the equation, okay, so when we take the equation 12 cosine squared theta equal 9, then the first thing we would do is divide out the 12. And so when we divide on both sides by 12, of course, we have cosine squared theta is equal to 9/12. Now, 9/12 is a reducible fraction, isn't it? Okay, let's see. 3 goes into 9 3 times and into 12 4 times. Okay. Now, if cosine squared theta is equal to 3/4, anytime we have something squared is equal to a number, then what we're squaring could either be positive or negative. So that's the reason we say plus or minus. And it would be plus or minus the square root of the number that cosine squared is equal to. So here's what we've got. The cosine of theta is plus or minus. Now, the square root of 3/4 is the same as the square root of 3 divided by the square root of 4. And the square root of 3 we can't simplify, but the square root of 4 we can. So we get cosine of theta is equal to plus or minus the square root of 3 divided by 2. Now, we're looking for the value of theta. See, that's what we're looking for. Theta is what? Well, here we know that we have two possibilities. The cosine of theta might be the square root of 3/2, or the cosine of theta could be the negative of the square root of 3/2. So here's what I'm going to do. I'm going to take this condition first, and then I'm going to look at this condition. And so when I'm looking at the idea of the cosine of theta being the square root of 3/2, then I'm thinking of my unit circle, okay? And in my unit circle, real quickly, we have a value of cosine that is positive. So I'm looking at a little smaller unit circle here just so I can get all of this in. So I'm looking at a second coordinate. Cosine of theta is represented by a first coordinate, isn't it? So I'm looking at a first coordinate on the unit circle that's positive. So that means it has to be in the first or fourth quadrant. Now, for the cosine of theta to be the square root of 3/2, that's a number that's almost 1. And so we would have a value, let's say, that is roughly here, and that's about where the square root of 3/2 is, because the square root of 3/2 is about 0.85. And remember, all the way to the edge of the circle is 1 unit. So I'm looking at angles, okay, that have a second coordinate, and I'm trying a first coordinate that corresponds with the square root of 3/2. So I'm considering an angle that would be right here, and that would be, remember, in a positive direction, that would be this angle, or an angle right here, and in this case, we're going all the way around to the unit circle, all the way around the unit circle, but not completely. Well, we ought to be able to figure out that this angle is pi over 6. And if that angle is pi over 6, the angle below is pi over 6 short of a full revolution. A full revolution is 12 pi over 6. If we're short, that's 11 pi over 6. Okay, so here's where we are so far. We understand that if theta is pi over 6, we have a solution because the cosine of pi over 6 is the square root of 3/2. Or theta could be 11 pi over 6 because the cosine of 11 pi over 6 is also the square root of 3/2. Now, that's only assuming that the cosine of theta is positive square root of 3/2. What about the scenario where the cosine of theta is negative square root of 3/2? Well, under those circumstances, the unit circle that we would consider, let's look here, we have a negative value for the cosine. So that means our first coordinate is going to be negative, and so we would have 2 points along the unit circle that would have that first coordinate. And that corresponds to an angle here and an angle here. Well, the very first angle would be the angle that we go there, and that's going to be pi over 6 short of pi. So this angle is actually 5 pi over 6. Now, the angle we see here in the third quadrant is the angle we get by going to here, and that's pi over 6 more than pi. And pi over 6 more than pi is 7 pi over 6. So we have two additional angles, and So we have these two additional angles. In this case, the cosine of 5 pi over 6 is negative square root of 3 over 2, and the cosine of 7 pi over 6 is also negative square root of 3 over 2. But we just need the cosine of theta to be one or the other, and so we actually have 4 solutions here. Now, let me tell you that it's not unusual for us to write those in the correct order. So I'm just going to come over here on the side and say, okay, well, look. This is the first, as we're making a revolution, this is the first angle we encounter. This is the second angle we encounter. This is the third angle we encounter. And finally, this is the fourth angle we encounter as we go from 0 to 2 pi. So if we write them in that order, which would be from smallest to largest, pi over 6, 5 pi over 6, 7 pi over 6, and finally 11 pi over 6. And that's the way most likely we would want to write our solutions. So, and of course, if we continued around the unit circle, we would have even more solutions, but we're only making one revolution. That was what we were told from the very beginning. Let's do another one that is a little twist on this idea, but we still have one single trig function. Notice we're continuing for this problem in the same theme or the same issues. We have one trig function, it's to the first power, that occurs one time in the equation. Now we're trying to solve for theta, and we're going to make sure that our theta solutions are between 0 and 2 pi. Possibly including 0, but not including 2 pi. 2 pi would be a repetition, wouldn't it? So anyway, but what we do first is isolate the trig function itself. And so in this case, we're going to add 3 to both sides first. So as we solve, if we're trying to isolate cosecant of theta, then we will add 3 to both sides. And of course, 3 plus 2 is certainly 5. And so we end up with 5 times cosecant of theta is equal to 5. Now we'll divide out the 5 on the left side. Whoops, my bad. Cosecant of theta is equal to 5 divided by 5. And so we end up with cosecant of theta is equal to 1. Now, quite frankly, what I would do next, this is the way I would approach this, because I have a real hard time dealing with the secant, cosecant, and cotangent. I like to have things dealing with sine, cosine, and tangent. And so probably what I would actually do next here is I would write cosecant as 1 over, we've got to remember this, sine of theta. Cosecant of theta is 1 over sine of theta. So we have 1 over sine of theta is equal to 1. Now, I need to deal with this so I don't have sine of theta in the denominator. So I'm going to multiply, each side by sine of theta. And so that will eliminate the denominator I have on the left side. And of course, we get cancellation, and so the left side becomes 1, and the right side is just 1 times sine of theta, which is sine of theta. In other words, the sine of theta is equal to 1. Okay, so now we've isolated a single trig function equal to a number. That's really the issue. And so we're looking for all of the positions around the unit circle where the sine of theta is equal to 1 in one revolution. Now the sine of theta being the second coordinate, then the only place the second coordinate is positive 1 is right here. And so the angle that we're talking about is the angle that puts us to that position. We're talking about this angle. And of course that angle is pi over 2, isn't it? And so in this case, there is a single solution. Theta is in fact pi over 2. the only solution to this particular equation. That is, the only solution between 0 and 2 pi. Okay, well, we're going to continue, but now we're going to make the equations a little bit more complicated, and we'll begin those on the next page. Well, now we move to a different technique of solving trigonometric equations. You see the equation we have here has only one trig function in it, but the trig function appears more than once. And the technique we're going to use here, since we have two terms and that function appears as a factor in each term, we see that the cosine of theta is a common factor. So a technique, this technique is solved by factoring. Now, the idea behind this is that this looks like, see, if instead of cosine theta we had an x, this would look like 2x squared plus the square root of 3x equals 0. And we could certainly notice there that we had a common factor of x, and we could factor that out. Well, we're going to think in terms of factoring a cosine of theta from the left side. So we end up with something that looks like this. Let's just follow the pattern here, though. If we had this expression or this equation that I just wrote down with x's in it, when we see that we have a common factor of x, we would factor that out, and we would end up with x times, in parentheses, 2x plus the square root of 3 is equal to 0. And then we would go about setting each of these factors equal to 0 separately and solving from there. So this is a technique that we're already used to. Well, our problem, of course, is a little different, but it's a very similar approach that we're going to use. We want to solve, here's our solution, or the way we're going to solve it. We've got 2 times cosine squared theta plus the square root of 3 times the cosine of theta equals 0. Now on the left side, we have this common factor of cosine, so we'll factor cosine of theta out. Okay, and what do we have? Well, in parentheses, we have 2 times cosine of theta plus the square root of 3 equals 0. Now, the significance at this point is that in the last set of examples that we looked at, we had one single trig function, and we solved for that trig function equal to a number. And then we could figure out theta. Well, when we're factoring out a common factor and we have one side equals 0, or factoring period, if we have a product of factors is equal to 0, then if anytime a factor is 0, we have a solution. So what we would do on the right side with saying x is equal to 0 and 2x plus square root of 3 is equal to 0, we do that here. We have a factor cosine of theta, and so we set it equal to 0, and we have a factor that is 2 times the cosine of theta plus the square root of 3 equals, and we set it equal to 0. And then we go about how we solve each of those. Well, for the cosine of theta equal 0, and we're only looking at values of theta between 0 and 2 pi, well, where is the cosine of theta equal to 0? It's equal to 0 when we're at this position or this position. And of course, we're talking about angles like this or like this. They have to be between 0 and 2 pi. And so this angle, the angle represented here, is if theta is equal to pi over 2. And the angle represented here is if theta is equal to 3 pi over 2. So those are two of the solutions to this equation. Now that's only dealing with that one single factor. when we look at the factor 2 cosine theta plus 3 equals 0 as an equation, then we solve for cosine of theta again. So we subtract square root of 3 on both sides. So this would end up looking like 2 times the cosine of theta is equal to negative square root of 3. And then we would divide out the 2, and so we'd have the cosine of theta is equal to negative of the fraction square root of 3 over 2. And so now we want to know, as long as theta is between 0 and 2 pi, what particular theta values that would be. So again, we look at a unit circle. At least this is my reference. Okay, whoops. Sorry about that. Here's my circle. Now, being negative means that the cosine of theta being negative means the first coordinate would have to be negative. And so we're over here, square root of 3 over 2 is about 0.85. And so we would be negative 0.85 would be roughly where I've marked it. And there's 2 positions on the unit circle that would have that first coordinate. So one is the angle that we would get here. And of course, that's where we're measuring in this fashion. The other would be the angle we get here. And that's how we measure in this fashion. And we already should understand where that is. I mean, that's because of the symmetry. We've been practicing this for quite some time. So this first angle would be when theta is equal to 5 pi over 6. And the second angle would be when theta is equal to 7 pi over 6. We've already seen those types of examples here already. So we have a total of 4 solutions, 2 that go with this factor and 2 that go with this factor. And so the solutions here, okay, would be in order. The first one would be pi over 2, what we have here, and then this one would be the next angle, and then this one, and then this one. So in order, we'd say pi over 2, 5 pi over 6, 7 pi over 6, and then finally 3 pi over 2. So we have 4 solutions to this equation. Well, let's continue on the next page with a little different variety here, okay? But it's still, we're going to use this factoring idea. So a lot of times when we have more than one occurrence of a trig function in an equation, then there's a good chance we'll be able to factor it because that's occurring more than one time. So good chance, like I said, that we might be able to factor it. So here we have the equation 6 sine squared theta minus 13 sine theta plus 7 equals 0, and we're supposed to find the solutions of the values of theta that make this true. Now, here we, of course, we have sine of theta occurring twice, and only the sine of theta, but it occurs in 2 different positions. But sine of theta is not a common factor here, is it? Because we have that third term plus 7, and there's no sine of theta factor there. But what I'd like you to note is the equation we see here looks similar to what we would have if we had had 6x squared minus 13x plus 7 equals 0. And that, of course, is a quadratic equation in the variable x. What we have above is a quadratic equation in the variable sine of theta. And the way we would solve this is by factoring. We would try factoring, and if we couldn't do it by factoring, we'd use the quadratic formula. So we're going to use this same idea, thinking of how would we factor the equation we have. So here's the way we're going to go about the solution. We're going to take our equation, 6 sine squared theta minus 13 sine of theta plus 7 equals 0. And we're thinking of it in these terms. So if we're trying to factor the equation with x's in it, we would think binomial times binomial is equal to 0. Now, let's imagine this, okay? Let's just come over here and just think about this if we were factoring this left side, just so that we have something to compare to. I think if we said 6x times x, we would certainly get 6x squared. And then if we said minus 1 here, excuse me, a minus 7 here, pardon me, and a minus 1 here, wouldn't that give us a negative 6x and a negative 7x for the middle, which would be negative 13x, and a negative 7 times a negative 1 would be positive 7. So we're going to mirror image that in our problem. This is what we're trying to factor. So we're going to say, let's say 6 times the sine of theta times the sine of theta will result in 6 sine squared theta. And if we put a minus 7 here and a minus 1 here, think what's going to happen when we multiply these together. We'll have negative 6 sine theta. When we multiply these together, we'll have negative 7 sine theta. And together, of course, that's negative 13 sine theta. And then negative 7 times negative 1 is positive 7. So we have it factored. Well, just like we would do in this case, we would set each factor to 0. Well, here, the two factors are 6 sine theta minus 7 and sine theta minus 1. So we take 6 sine of theta minus 7 and set it equal to 0. And we also take the sine of theta minus 1 and set it equal to 0. Now over here on the right, let's deal with this one right away. We'll isolate sine of theta just like we've been doing by adding 1 to each side. So we have sine of theta is equal to 1. And when we look at the unit circle and decide where that happens, oh, the sine of theta is equal to 1 only in this position. The angle here, which is, of course, the angle pi over 2. That's the only place the sine of theta is equal to 1 in between 0 and 2 pi. So one solution is pi over 2. Now when we look over here on the left side and we isolate sine of theta, the first thing we would do is add 7 to both sides. And then the next thing we would do is divide both sides by 6. Now, let's remember that the sine of theta, let's see, this is a big note here. Recall that the sine of theta always gives a value that is bigger than negative 1, bigger than or equal to negative 1, and less than or equal to positive 1. The sine of theta always has to be between negative 1 and 1. And look what we have here. We have the sine of theta is 7 over 6. And 7 over 6 is bigger than 1, isn't it? So that means there's no theta that can give us the value 7 over 6 when we take the sine of it. So there is no solution to the equation that we have right here. No solution to that equation. So in other words, that factor doesn't generate a solution. Hence we have only one solution, and that's the solution that we got based on the factor sine theta minus 1. So the solution, okay, the solution is the single value of theta, which is pi over 2. So that's a very important thing, not only to notice how we solve this, but be on our toes, that if we get something like the sine of theta is a number bigger than 1 or smaller than negative 1, then we can't go forward with that idea. Well, this equation adds a new complexity. And the complexity that we have here is this is the first time we've had two trig functions in one equation. Now, and when we look at this equation, there's no opportunity for factoring out a common factor, because we certainly don't have a common factor between sine squared theta and cosine squared theta. So we have to do something new. Now let's kind of, in our mind, go back and think of what we've done. The very first group, we had one trig function, and we could isolate it. We had one trig function that only occurred one time, and so we got that trig function alone equal to a number. In the last couple of examples we've looked at, we've had 0 on one side of the equation. That was the first thing. And we could either factor out a common factor. That trig function occurred more than once, but it was only one trig function. And in one case, we factored out a common factor. In the other case, we factored it like a trinomial, the left side. And so we have to deal with this, which neither one of those techniques works directly. Now, let me point out to you that normally when we have more than one trig function, we try to create an equation, okay, try to create an equation with a single trig function. We've seen several examples. That's what we've done so far, and it's worked for us. I mean, that we haven't created that situation. That's what we've had. So try to create an equation with a single trig function. In other words, only sine, only cosine. And it may occur more than once, but we want to have only one trigonometric function, unless we can factor ahead of time. And so a lot of times what we will do, and we could use either case here, let me make this note. Since sine squared theta plus cosine squared theta is equal to 1, that's that very important Pythagorean identity, isn't it? We could convert either sine squareds into cosine squareds or vice versa. See here, if I subtract cosine squared theta from both sides, I end up with sine squared theta is the same as 1 minus cosine squared theta. So if we look at this sine squared theta, we could replace it with 1 minus cosine squared theta, and then we would have an equation that only had cosines in it. So that's how we're going to go about doing this. Okay. We're going to take our equation, sine squared theta plus 5 times cosine squared theta equal 2. And in this place right here, we're going to replace it with 1 minus cosine squared theta. So with 1 minus cosine squared theta in the place of sine squared theta, then we still have plus 5 cosine squared theta equal 2. Now, we can combine the cosine squared thetas. And on the one hand, we have a minus 1 of them here, and we have a positive 5 of them here. So negative 1 plus 5 is 4. So this is 1 plus 4 times times cosine squared theta equal 2. Now we can solve for cosine squared theta. So we subtract 1 on both sides, and when we do, we'll have 4 cosine squared theta is equal to 2 minus 1, which is just 1. And then we would divide out the 4, so we would have cosine squared theta is equal to 1 over 4. And so cosine of theta would be plus or minus the square root of 1 over 4. But the square root of 1 over 4 is the same as the square root of 1 over the square root of 4, isn't it? And that ends up being the same, of course, as 1/2. So we have the cosine of theta is equal to plus or minus 1/2. So that we really have two equations here. See, this is really cosine of theta is 1/2 along with cosine of theta is equal to negative 1/2. So let's consider cosine of theta is equal to 1/2. And let's consider the unit circle. Now, for the cosine of theta to be equal to 1/2, we're going to have a positive, okay, a positive first coordinate of 1/2. We're looking for the angle so that we have a positive first coordinate of 1/2. And then here's where the first coordinate 1/2 would be, and that represents this position on the unit circle and this position. Both of those have a first coordinate of 1/2, if this is where 1/2 is. So we have an angle that looks like this and an angle that looks like this. Well, of course, to get to here, we go from this position to this position, and that angle is an angle of theta that is pi over 3. Now, the angle that we see in the fourth quadrant we get by going around this direction. And that angle, we ought to be able to figure that out. However, we're going to do this. That angle will be 5 pi over 3. We can count them off, or we can think that, oh, this is pi over 3 this direction. And so we're pi over 3 short of being all the way to 2 pi, which is certainly 5 pi over 3. So we have two solutions so far. Now, that was only dealing with the cosine of theta being positive 1/2. If the cosine of theta is equal to negative 1/2, then our unit circle and our reference positions would be in the second and no, I'll give that up again. I did that earlier. Would be in the second and third quadrant, because we have a negative 1/2 first coordinate, and that would be represented by a position here or a position here. So we're talking about either this angle or we're talking about this angle. Now, this angle at the top would be where theta is equal to 2 pi over 3. And this angle at the bottom would be where theta is equal to, let's see, 4 pi over 3. And so if we write these in order, you see this would be the smallest, then this would be the next one, this would be the one after that, and then this would be the last one. So the solutions that lie between 0 and 2 pi are the values of theta that are pi over 3, 2 pi over 3, 4 pi over 3, and finally 5 pi over 3. So we actually have 4 solutions here. And what did we do? We used an identity to convert to one, and that's really, notice that. We used an identity to convert to a single trig function. And that's something that we probably do often when we're solving trigonometric equations. So in the equation that we're to solve here, we kind of have the same dilemma that we had previously. We have two different trig functions, and we would like to have one single trig function. And so we need to either convert sines to cosines or cosines to sines. And the only real tool we have, we can't convert a sine to the first power or a cosine to the first power. We can only convert sine squared to the first, sine squared or cosine squareds. And it's all based on, once again, the fact that sine squared theta plus cosine squared theta is equal to 1. That can change. See, that gives us two possibilities. We can subtract cosine squared theta from both sides and end up with this new identity, which means any place we see a sine squared theta, we can replace it with 1 minus cosine squared theta. On the other hand, if we take this identity and we subtract sine squared theta on both sides, we'd end up with cosine squared theta on the left and 1 minus sine squared theta on the right. So that tells us that we could take any cosine squared theta and replace it with a 1 minus sine squared theta. So we can convert from one trig function to another. Well, what we have, okay, is sine squared theta equal 3 times cosine theta plus 1. Now we can't mess with the cosine of theta, but the sine squared theta we can convert into 1 minus cosine squared theta. So as we go about solving this, the way we would come up with our solution is that we would try to get only one trig function, and our only hope is to only get cosines by replacing sine squared theta with 1 minus cosine squared theta. So the left side is 1 minus cosine squared theta, and equal to the right side, which is 3 times cosine theta plus 1. Now, as I'm looking at this, I see cosine squared theta, and I see cosine theta to the first power. That's kind of like an x squared and an x to the first power. So I think that this is really a quadratic equation in the variable cosine of theta. So what I'm going to do is I'm going to simplify and gather all terms to one side, get 0 on one side. So I'm going to multiply that 3 out. I have 3 times cosine theta plus 3 times 1. Now, why don't we get 0 on the left side, okay? And then, so we won't have to worry about that minus cosine squared theta. So I'm going to do this. I'm going to subtract a 1 and add a cosine squared theta to both sides. And when I do, this side will be 0, and this side, which we started as 3 cosine theta plus 3, if I subtract a 1 on both sides, and I've got a minus 1 here, and if I add a cosine squared theta to both sides, I have a plus cosine squared theta there. And then it's a matter of rearranging. You see, I'm going to put the cosine squared theta in the beginning, and then I'm going to put the plus 3 cosine theta, and of course I have a 3 minus 1, which is a 2, so I have a plus 2 in this position. And so just to think about this, this is like an x squared plus 3x plus 2 that we ought to be able to factor. So we're factoring, though, not x's, but things that involve cosine. So I'm going to say cosine theta times cosine theta. It's factoring it like we would normally a trinomial. And certainly when we multiply those, we get cosine squared theta. And then I'm going to just try a plus 1 and a plus 2. And certainly the 1 times the 2 gives us the 2, and the cosine theta, the cosine theta times 2, along with the 1 times the cosine theta, gives us 3 cosine theta for the middle. So it is factored correctly. Well, I have a product of 0, so either factor could be 0. So I take the first factor, set it to 0, take the second factor, set it equal to 0, and solve appropriately. So here, the way I'm going to solve is I'm going to isolate the cosine of theta by subtracting 1 on both sides. So I get cosine of theta is equal to negative 1. And when I look at the unit circle and try to decide where that happens, well, cosine of theta is negative 1 at this position. That's the only place we have a first coordinate that's negative 1. Well, what angle is that? Oh, that's the angle pi, isn't it? So I know pi is a solution. Now when I look over here to the second factor, cosine of theta plus 2, and I set it equal to 0, I'm going to similarly isolate cosine of theta. But when I have cosine of theta is negative 2, there is no place on the unit circle where the first coordinate is negative 2. You know, because what do we know? I mean, we've got to remember this, but here's the situation. if we had a unit circle, this is where -1 is, and we're not beyond that. If we're on the unit circle, we can't go beyond that. So this is the other big issue that we should always keep in mind. The cosine of theta always has to give a result that is between -1 and +1. And so there's no way the cosine of theta can be equal to -2, so there's no solution to this intermediate equation that we have there. But we already have a solution to the equation that we have on this side, and so that means we have a solution to the equation. So our solution is the one single value of theta that is simply pi. Now, I hope you understand, I have not done this on any of the problems, but we could certainly check. I haven't done it, okay? But we could check. And some of those problems, we've got lots of values of theta. But what do I mean by check? Well, it says if we put a pi in the place of theta, then we have a solution, and so our equation should be true. So let's see. Let's replace theta with a pi. We don't really know about the truth. We're assuming it's true because we found that as the solution. Well, remember, sine squared pi really means find the sine of pi and square that result. We'll keep that in mind here. Now, the sine of pi is 0, so on this side we have 0 squared. And the cosine of pi we just talked about is -1. So on the right side, we have 3 times the parentheses -1 plus 1. And of course, 0 squared is 0, and -1 plus 1 is 0. So on the left we have 0, and on the right we have 0. So we've verified that we do have, in fact, a solution when theta is pi. Now, we weren't asked to check it here, but it's nice to know what we're doing really does, in fact, give us a solution. Okay, let's look at another example before we go on to yet additional type, and we'll do that on the next page. So here you see our equation is cotangent squared theta equal 3/2 cosecant theta, and we're to solve on the interval from 0 to 2 pi, including 0 but not including 2 pi. So back to that idea of one revolution. Only each one of these equations we've had so far has an infinite number of solutions. It just has a finite number of solutions that are in one positive revolution between 0 and 2 pi. Now, here again we have two different trig functions in one equation. And my preference is to have one single equation trig function if we can. And in addition, I prefer to have an equation involving sine and cosine. Now, that doesn't mean we can't have others, but I prefer that. And so when I look at this equation that we're to solve, the first thing that comes to my mind, with just some notes over here, the first thing that comes to my mind is that the cotangent of theta is the cosine of theta divided by the sine of theta. And so cotangent squared theta is really nothing more than the cosine of theta over the sine of theta squared. And the other thing that I'm thinking is that cosecant of theta can be written in terms of sine of theta. That's 1 over sine of theta. So I could replace cotangent squared theta, and I can replace cosecant theta with things involving only cosines and sines. And that's my preference. Doesn't mean that's what we have to do here, but that's my preference. So when I'm going about solving, okay, this equation, cotangent squared theta equal 3 over 2 times cosecant of theta. As described over on the right, I'm going to replace cotangent squared theta with the cosine of theta over the sine of theta squared. And that's equal to 3 over 2 times cosecant of theta, which I'm replacing with 1 over sine of theta. Now on the left side, when I square a fraction, I square the numerator and the denominator. So the left side is cosine squared theta divided by sine squared theta. And of course the right side is the fraction 3 over 2 times sine of theta. Okay, so we still have an equation that has two different trig functions in it, and if I'm trying to solve an equation anyway, I try to get rid of denominators where the variable is. And so in this case, I need to multiply both sides of the equation by something that will cause a reduction of, a cancellation of the denominators, if you will. And so we look at the two denominators, sine squared theta and 2 sine theta, and recognize that we're going to have to multiply by a sine squared theta to get the left side reduced. But when we multiply the right side by sine squared theta, the sine in the denominator will also cancel, but we'd still have a 2 in the denominator. So we'll do one more thing. Let's multiply both sides by 2, and the 2 in the denominator on the right side will cancel, won't it? So here's what we're doing. We're multiplying both sides by 2 times sine squared theta. So when we multiply the right side, it would look like this. And when we multiply the left side, it would look like this. Excuse me, the left side and the right side, I mixed those up, didn't I? So in this case, we get the sine squared thetas canceling, and we're left only with the 2 times the cosine squared theta. Now over on the right, we get the 2's cancel, and we have sine squared theta over sine theta, which is just sine of theta. It's like x squared over x, that's just x. So on the right side, we have 3 times sine of theta when we reduce that side. You know, again, what we ended up with is 3 sine squared theta over sine theta. And that's 3 times the sine of theta squared over the sine of theta. And so that's why I said that this is just 3 times the sine of theta, because one of these factors of sine of theta cancels with what's on bottom, doesn't it? Okay. So here's what our equation looks like now. We still have 2 trig functions, but it certainly looks better, doesn't it? Now, what we have to worry about at this point, though, is that we've got to be concerned about converting into one trig function. And we have the mechanical way to do that by rewriting cosine squared theta as 1 minus. See, we're going to rewrite that as 1 minus sine squared theta. So when we make that replacement, the left side will be 2 times, instead of cosine squared theta, 1 minus sine squared theta. And equal to 3 times sine theta on the right. Now the significance now is that we have only one trig function. On the left side, when we multiply that out, we're going to have a 2 minus a 2 times sine squared theta is equal to the right side, which is 3 sine of theta. Now this looks similar to something that we've been doing. So here's what I'm going to do. I'm going to gather all terms to the right side. And so I'm going to get 0 on the left. And to get 0 on the left, I have to add a 2 sine squared theta on both sides. Okay, and I've already got the plus 3 sine theta over here. and I need to subtract a 2 on the left, so I've got to subtract a 2 on the right, and so it ends up looking like this. Oh, let's see what we're going to do here. Well, I think as we investigate here, see, we're thinking of this as like 0 is equal to 2x squared plus 3x minus 2. And so we're looking at how we would factor this. But instead of x's, we have sine of theta. So I'm going to suggest 2 times the sine of theta times the sine of theta. That's how we get 2 sine squared theta. And then I'm thinking we need a minus 1 and a plus 2. And certainly this portion right here gives us the negative 2, doesn't it? And this portion, of course, right here gives us the 2 sine squared theta. Now here we get 4 sine theta, and here we get negative 1 sine theta. And when we add negative 1 and 4, we get 3, which is what we have. And so my point here, of course, is that we do have it factored correctly when I show it factored in this fashion. So I kind of caught myself here, haven't I? Let's come over to here now and deal with setting each of those factors to 0. So I take 2 sine theta minus 1 and set it to 0, and I take sine of theta plus 2 and set it equal to 0. Well, let's get this one out of the way real quickly. When we solve for sine of theta, we get sine theta is negative 2, and we just have talked about that. There's no solution in that situation, is there? But here on the left side, what we would do is we would add 1 to both sides first. We're trying to get sine theta alone. And then we would divide on both sides by 2. So we'd get sine of theta is 1/2. Now, when we consider a unit circle that would be associated with that, then it would be a sine value that's 1/2, and a sine value is the second coordinate. And so if that's where 1/2 is, we would have 2 positions on the unit circle that have a second coordinate of 1/2 here and here. And this is the angle pi over 6, and this is the angle 5 pi over 6. And so the answer, the solution, or the answer here would be theta can be pi over 6. We'd have a solution. Theta could be 5 pi over 6. We have a solution. So this is a pretty important problem. We've used a whole lot of different techniques in one single problem, didn't we? But we certainly did get a valid solution here. 2 solutions in the interval from 0 to 2 pi. We're going to pick up here next. We're going to start now looking at the infinite number of solutions and see how we'll deal with something in that fashion when we have an infinite number of solutions, rather than just looking at solutions that are between 0 and 2 pi. And that's what we'll work on next.